So here we are going to discuss mostly the questions, important questions. First question, let's start with the first question. Read the question first. A farmer purchased 100 heads of the livestock, okay, for a total cost of rupees 4,000. The prices were as follows: cows at the rate rupees 120, lambs at the rate rupees 50, pigs at the rate rupees 25. If the farmer obtained at least one animal of each type, how many each did he buy? How many each did he buy? That is what you need to find out only. Understand this thing. First, what you need to find out, how many types of animals of each type, how many of each type he did buy. Okay. And so first of all, whatever is given, let's write this down first. It's mentioned that the farmer purchased 100 heads of livestock for a total cost of 4,000. So total cost is 4,000. Okay. And the prices for each animals were given, calves, then lambs and pigs, and also all these things are given. So basically, suppose for instance, if I denote this calves by C, okay, this lambs by, let's say, L, and let's say pigs by P. Suppose we denote these notations so that we can just simply put this in the equations, whatever equations we are going to create. So definitely, since they have mentioned that the total cost is 4,000, so definitely you will get this equation 120C plus 50L plus 25P is equals to 4,000. These are the divided cost, and total cost of this thing has been mentioned to be 4,000. So definitely this will be 120C plus 50L plus 25P is equals to 4,000. That is what is given in this case. Okay. And this is a Diophantine equation of three unknowns. This is a Diophantine equation of three unknowns. But you don't know how to solve the Diophantine equation of three unknowns. You know the Diophantine equation of two unknowns. So what we do is we need to convert this into two unknowns and then we have to solve. For which definitely you will need one more equation. Obviously, one more equation so that we can just simply substitute this in the value of in this equation so that this simplifies to an equation of two variable. Okay, two unknowns basically. Is this thing is given that a farmer purchased 100 head of livestock. 100 head of livestock. Okay, so total heads are basically 100. Livestock is there, livestock under which you have calves, lambs and pigs and all these things are there. So total there are 100 head, which means that total calves plus lambs plus this pigs, this is equals to 100. So this relation is given, C plus L plus P is equals to 100. So definitely we can get the value of P from here. P or anything you can just simply find out. So we can get the value of P from here. Let's find out what is P from here. What is P from here? P is basically 100 minus C minus L. So simply take this P and put this in the first equation. So this turns out to be 120C plus 50L plus 25 multiplied by 100 minus C minus L is equals to 4,000. Simplify this thing. If you simplify this, you have 120C. Okay, and over here, how much? 120C and 25C, which means this is 95C. 95C and 50L minus 25L, which means this is plus 25L. Okay, plus 25L, and this is equals to 2,500. So 4,000 minus 2,500, that is basically 1,500. So this is your simplified equation. You have to solve for C and L. You have to solve for C and L, and definitely whenever you're solving the Diophantine equation, just like you simply find out the general solution and simply put this over here, definitely you will get the general solution, but you have to find out the positive solution in positive integers because these are always positive. C and L is always positive because C stands for calves. The number of calves can't be negative. Okay, so obviously you have to solve for the positive solution as well. So what we do in this case, let's solve this. Let's solve this Diophantine equation. This is a typical Diophantine equation, basic one. You can consider CL or XY, whatever. Let's solve this. But for that particular part, you need to see that what is the GCD of 95 and 25. So anyways, you have to find out this GCD. So best is the Euclidean algorithm, because anyways, whatever you do, you need to just use this particular Euclidean algorithm, right? From there, you will get the last non-negative, non-zero remainder, which you will require in this case. Okay, so let's start with this Euclidean algorithm. What is that? You start with the largest number. Okay, start with the largest number and try to express that. You just simply try to express that in terms of the divisor to be 25. And one more thing, it is necessary that for this Diophantine equation to be solvable, either you convert this or you can directly solve this 95, 25, you can directly solve this, or you can simplify, cancel out 5 and all, you can do that. Let's solve this directly only. In case if you want to simplify, that is also fine. 95 and 25 is there. GCD of 95 and 25, because this GCD 1500 should be divisible by this particular GCD. Otherwise, this is not possible. D divides this thing. Whatever is this D, GCD of A and B is equals to D. And if D divides C, then that is solvable. Otherwise, not. Okay. Now, clearly, you can see that this is by basic observation. You can see that GCD is 5 only. GCD is 5 only. Greatest common divisor is 5 only. But let's see this by the Euclidean algorithm. Let's start with 95. 95 is there. So 95 is, you keep the divisor as 25. So 25 into what? 25 into, 25 into 3. 25 into 3 plus 20. Right? 25 into 3 plus 20. Okay. Then 25 comes down. Okay, 25 comes down. 20 comes down. So 25 now divisor is 20. So 25 is what? 20 into 1 plus 5. 20 into 1 plus 5. Okay. Still remainder is not 0. So bring this 20 down. Right? 20 is equals to, divisor is 5 now. And this is a complete multiple of 5. 20 is a multiple of 5. So 5 into 4, 20. And remainder is now 0. So last non-zero remainder is 5. This is your last non-zero remainder, which means GCD of 95 and 25 is basically 5. Okay. So now what you are going to do? You are going to express this in linear combination of this C and L, right? So you need to find out this particular solution. Why we are doing this thing? We are doing this thing for just to find out this particular solution C and L. To represent this, start with the last non-zero remainder. 5 is equals to what? 5 is equals to 25 minus 20 into 1. Okay. Next we have 25 minus 20 into 1 hollow. Then 20 is what? 20 is 95 minus 25 into 3. So 25 minus, we can write this to be 95 minus 3 into 25. Right? Again simplify. 25 minus 95 minus 3 into 25. So 25 plus 3 into 25, 95 into minus 1, right? Because you need to express into this form 95C plus 25L. So 95 into minus 1, okay, plus 25 into 4, plus 25 into 4. Clear? 95 into minus 1 plus 25 into 4. Left hand side, you have 5. So 5 equals this thing. But what you need? What you need actually? You need 1500. You need 1500. So multiply with 300. Left hand side should be 1500, but we have 5. So multiply with 300. So this turns out to be 1500 equals 95 into minus 300 plus 25 into. So this thing becomes 1200. Okay, clear? So your particular solution, what is the particular solution? Particular solution is C naught, let's say. C naught is basically minus 300. Right? Compare this thing. These are all your particular solution. Minus 300 and 1200. C naught is minus 300. And L naught, let's say. L naught or Y naught, which is 1200. Okay, so these are your particular solution. These are your particular solution. But definitely these are particular solutions. You need to find out their positive solutions. What we do for positive solution? We find out the general solution and make this greater than 0, right? So find out the general solution. What is the general solution? Find a general solution. What is the general solution? If you remember, that is fine. General solution of a Diophantine equation, Ax plus By is equals to C, or in this case Ac plus Bl is equals to K, let's say. What is the general solution? C is equals to C naught plus B by D into T, right? D stands for GCD of AB, and L is basically L naught minus A by D into T. We have discussed this thing, general solution. In terms of X only, X is what? X naught plus B by D into T, and Y is basically Y naught minus A by D into T. So what is C naught? C naught is minus 300. So find out what is C. C is basically, what is C in this case? C is basically minus 300 plus B by D. What is B? What is B in this case? B is 25, right? B is 25. Okay. Initially, what you can do is you can write it down. D is 5. Okay. D is 5. This is D. GCD is 5. Okay. What else? D is 5. What else? A is 95. B is 25. Okay. B is 25. So put this value. So C naught, you know C naught. C naught, you can write it down over here itself. C naught is minus 300 and L naught is 1200. Which means C is what? C is minus 300 plus 5T. Right? B by D. Okay, B by D into T. Okay. And 25 by 5, that is basically 5T. And L is what? What is L? L hoche, this is 1200 minus A by D. A by D means 95 divided by 5, that is 19, minus 19T. So these are your general solution. These are your general solution. This is your general solution. Why this is needed? Why general solution is needed? General solution is needed to find out the positive solution. How many positive solutions are there? What we do in case of positive solutions? We just simply make this greater than 0 and find the possible values of T for which this is positive. So for positive solution, what we do? Minus 300 plus 5T is greater than 0. And 1200 minus 19T is greater than 0. Now find the range of values of T from here. Now from here clearly T is greater than 60, right? And from here you will get T is less than 1200 divided by 19. Mane around 1200 divided by 19. Around 63.16. 63.16 in decimals. Okay, 63.16. So definitely combine these two and find the integer values. T is what? T is, first of all, T in this case belongs to Z. Integers. Integer values basically lying in between this interval. Corresponding to this value of T. Find out what is T. Combine these two. T is greater than 60. From here you will get 60 less than T. You will get 60 less than T. Combining these two inequalities, we have T less than 1200 by 19 minus 63.16. So T being an integer, the possible values of T are, and also T lies between 60 and 63.16, which means T is basically 61, 62 and 63. So these are the corresponding values of T, with respect to which we'll get the different values of C, L and P. We already know what is C, L, and P. We have found already the relation with T. So we'll simply put all these values and simply find out the values of C, L, and P. Okay, so for instance, let's say for the first case, when T is equals to 1, sorry, when T is equals to 61, then what will we see then? C is what? C is this thing, minus 300 plus 5T, which means C is basically minus 300 plus 5 into 61. So that is how much? So this is minus 300 plus 305 actually. So the difference is 5. So this is 5. So C is 5 in this case. And similarly, we can find out what is P also. L and P as well. Let's find out L. L is what? L is basically 1200 minus 19T. Okay. We can replace the value of T over here. (19T), that is T is 61, so 19 into 61. Okay, and after calculation, whatever, I think this is this will be around 41, I guess. Okay, and similarly we can find out P as well. Okay, what is P? P we can get it from the previous relation, that one which we have found out, this one. From here we can find out what is P. P is 100 minus C minus L, so this is basically 100 minus 5 minus 41. Okay, so this must be 54. P must be 54. Okay, so similarly we can find out the remaining values as well, the remaining set of possible values, right? Clear? What I mean to say is this one. Let's say for instance T is equals to 62. When T is equals to 62, we can find out the next possible sets of values. C is equals to what, L is equals to what, and P is equals to what. Similarly for T is equals to 63, you will get the remaining sets of possible values. Okay, and those are your sets of possible values will be your answer. Fine. Very basic question on Diophantine equation, although nothing much over here, just calculations. Show that any integer of the form 6k plus 5 is also of the form 3m plus 2, but not conversely. Obviously, you will say that this is a question of division algorithm. Definitely 6k plus 5, 3m plus 2, they are trying to show this thing. Obviously, it's a question of division algorithm. Now, question is how will we proceed in this case with the help of division algorithm? Okay. So we are going to show that any integer is of the form 6k plus 5 is also of the form 3m plus 2, but not conversely. Okay, so which means that we have to show that this is equals to 3m plus 2, but not the converse is not true. Converse is not true. 6k plus 5 is equals to 3m plus 2. That is what we need to show, which means that in division algorithm, you know that A is equals to BQ plus R, right? B stands for divisor, A is dividend, Q is quotient, R is remainder, or whatever you have in your notes. B is equals to AQ plus R, whatever you have in your notes, accordingly I'm saying. A is equals to BQ plus R or B is equals to AQ plus R. Same thing. B stands for divisor, Q stands for quotient, R stands for remainder. Left hand side you have dividend. Dividend is equals to divisor into quotient plus remainder. This is the concept of division algorithm. So what we do in this case, let's take B is equals to 3, money A is equals to 3k plus something, 3k plus remainder basically. Suppose in division algorithm, what we are going to do, in division algorithm, put A is equals to k or B is equals to 3, suppose. Okay, put A is equals to k and B is equals to 3. So therefore, there exist unique integers. There exist unique integers by division algorithm Q and R such that, let's say k is equals to 3q plus R. This is by division algorithm we are seeing, where R lies between 0 and 3. R lies between 0 and 3. So what are the possible values of R? The remainder basically, R can be 0, 1 or 2. R can be 0, 1 or 2. Okay, which means that this particular K can be of the form, K can be of the form 3Q, 3Q plus 1 or 3Q plus 2. 3Q, 3Q plus 1 or 3Q plus 2. So now just simply take and simply prove this thing, nothing else. Simply just prove this thing, whatever you have. Case 1, what is case 1? Case 1, if K is equals to 3Q, let's say. We are going to show that if K is equals to 3Q, then 6K plus 5 is of the form 3M plus 2. So multiples of 3 plus 2, remainder is leaving to be 2. So K is equals to 3Q, let's say, which means that 6K plus 5, what is 6K plus 5 then? 6 into 3Q plus 5, put the value of K, so 6 into 3Q plus 5, which is 6 into 3Q. We can write this 5 as 3 plus 2, so that we can take out one 3 common. This turns out to be multiples of 3 now. So 3 into 6Q plus 1 plus 2. So remainder is left out to be 2. So we have 3M plus 2, 6Q plus 1. What is 6Q plus 1? Integer only. Some integer. M is what in this case? An integer. So which means that over here, this is of the form 3M plus 2, where M is equals to 6Q plus 1. This is already of the form 3M plus 2. Clear? Similarly, case 2. You all can try out case 2. What is case 2? What happens if K is equals to 3Q plus 1? 3Q plus 1. So simply once again check for here. We have 6K plus 5. So 6 into 3Q plus 1 plus 5. Okay. Which means that multiply this thing 6 into 3Q. And this is 6 plus 5, which is 11. Which means that again write this as 6 into 3Q. And write this 11 is there, so write this as 9 plus 2. Why will write this as 9 plus 2? Reason being, from this particular part, 3 will come out as common. You need 3, not 6. You need 3, so take out 3 common. Right? So this becomes 3 into 6Q plus 3. Okay. Plus 2. So now this is of the form 3M plus 2. Now this is of the form 3M plus 2, where M is 6Q plus 3. M is integer only. And similarly, last case, case 3. What is case 3? What happens if N is equals to 3Q plus 2? N is equals to 3Q plus 2. So for 3Q plus 2, not N, K basically. K is equals to 3Q plus 2. So K is equals to 3Q plus 2. So once again, same thing, similar process. 6K plus 5. 6K plus 5 is equals to 3 into 6 into 3Q plus 2 plus 5. We need to bring this into the format of 3M plus 2. Same logic, multiply 6 into 3Q plus 6, 12 plus 5, that is 17. Write this 17 as 15 plus 2. Write this 17 as 15 plus 2. So this turns out to be 15 is there. Now 3 will come out 3 as common. So this turns out to be 6Q plus 5 plus 2. Once again, this is of the form 3M plus 2. So these are the cases. Case 1 is K is equals to 3Q. Case 2 is K is equals to 3Q plus 1. And case 3 is K is equals to 3Q plus 2. So definitely, you can see that every time for each of these cases, every time you're getting 6K plus 5 is equals to 3M plus 2. But the converse is not true. Now you all will try the proof for the converse. you all will show that the converse, which means that 3m plus 2 cannot be represented in the form of 6k plus 5. I hope the converse will be easy for you. You all will be able to prove the converse. You all will prove that 3m plus 2 cannot be represented every time in terms of 6k plus 5. Okay. Converse is not true. Converse is not true. You all prove this. Converse is not true. I hope this is clear. Quite easy. Simply basic applications of division algorithm. Chalo, next question. I hope that is clear. Previous one is clear. Next question from ISI Entrance 2011. Consider three positive real numbers a, b, and c. Show that there cannot exist two distinct positive integers m and n such that both of these equations holds. When simultaneously they can't be hold. They cannot hold simultaneously for two distinct positive integers m and n. Okay, that is what we need to show over here. Now there are various proofs for this particular thing. A lot of methods are there for just proving this thing only. What we do in this case, they have asked to simply show that they are not simultaneously holding. The best possible way of proving. So first of all, you understand this thing in ISI Entrance. To answer the subjective paper, to prove certain things, let's say, to prove certain number theoretical proofs, or let's say certain combinatorics proofs as well. Mostly you will find this logic in number theory, inequalities, combinatorics, and maybe in certain typical questions of geometry if they have asked to prove something, show that, prove that. One very best method of proving is the method of contradiction. You take some assumption, show that that is not true. Later on, you just prove this thing with your logic and simply show that whatever assumption you have conducted, like you have considered, that is wrong basically. That is known as contradiction method. Very, very important. You will find for the past few years, lot of questions has been asked from basic contradiction. Prove by contradiction. Definitely they'll not mention that you have to prove by contradiction. You have to understand that whether this have to be proved by contradiction or not, obviously. Right? So what we do is we prove by contradiction, nothing else. Okay. Only proof is by contradiction. Let's see one proof, and later on if there are any other proofs possible, we can see that as well. But let's start with the proof itself. Whatever we have, let's prove by the method of contradiction. Method of contradiction. Okay. So before that, definitely, whenever you are starting a question based on method of contradiction, you want to prove by contradiction, so you have to consider certain assumption based on the questions only. But your question will only state that what assumption we have to take. Question itself will state that what assumption we have to take. If you read the question, think on this thing. Now basically what happens is from 11th and 12th standard, mostly students practice a lot of objective type questions and all, until if you are preparing for RMO, pre-RMO and INMO examinations in your 10th and 11th standard, then this is fine, you are in touch with the subjective type questions somehow. But definitely, but students when they go to class 11th and 12th, mostly they focus on the objective type questions, what happens after 11th and 12th. So this method of contradiction, maybe you have done certain proofs based on method of contradiction long time ago, but definitely here in ISI Entrance, most of the questions I have seen in many every year, there may be certain question which can be solved by method of contradiction. Anyway, so let's start with this thing. What assumption we are going to consider, and from where to understand we have to consider this assumption, because they have said that there cannot exist two distinct positive integers m and n such that both of these holds, which means that Since they have mentioned this thing that two distinct positive integers, the first assumption will obviously come that this is m is greater than n or n greater than m. Any of this thing, n greater than m or n greater than m. Any of this assumption you are considering, because since they have mentioned that m and n are distinct, so any of them has to be bigger. Either n is bigger or m is bigger. Any of them are bigger, right? So with this particular thing, and obviously it's mentioned that m and n are in positive integers, which means m and n belongs to z plus positive integers. A, B, C are real numbers. A, B, C are real numbers. Okay. So any of this assumption you can consider m is greater than n or n is greater than m. Any of this assumption you can consider. Accordingly, we'll proceed from here. Okay. Clear? Positive real numbers, which means R plus. So let's take this one only. Let's take n is greater than m. Let's see this one. You can also take m is greater than n. So let's n is greater than m. Let's say. Let's see what we can get from here. If n is greater than m, first of all, understand this relation is given. One of these relations, you write this down. First, you have this relation a to the power m plus b to the power m is equals to c to the power m. So since you have assumed that n is greater than m, so definitely from these two relations given, from the first one, we can get one conclusion. Definitely c to the power m will be greater than a to the power m. Obviously, c to the power m, a to the power m plus b to the power m is c to the power m. n is greater than m, no problem. You have this relation. Adding these two, you are getting this number. So definitely c to the power m is greater than a to the power m. Obvious reasons. Okay, c to the power m is greater than a to the power m. So what we can say from here? If c to the power m is greater than a to the power m, can we say if these two are greater, then definitely c is also greater than m. C is also greater than a. Okay, c is greater than a from here. Also, c to the power m is also greater than b to the power m. This is also true, which implies c is greater than b as well. So all possible relations I'm going to write it over here. Later on, what we are going to see from here, this depends on the exposure of your problem and your observation of the problem. You're observing the problem. These are nothing but informations what you have. These are hidden informations of the questions. Hidden information of the question. Observe the question. You see the question. And you write down these informations first, whatever you can see from here. Okay. Clear? N is greater than m, which means obviously from here something you have to do so that we can prove that this is not simultaneously holding, such that both of them holds. When it does not hold, we have to show that there cannot exist two distinct positive integers. Distinct integers we have considered. We will see that these two are simultaneously not holding for considering distinct positive integers. Okay, questions take ghuriye bole chhe. They have twisted the question and they have mentioned that cannot exist two distinct positive integers such that both of them holds, which means that you have to show that distinct positive integers, these two conditions given, equations given, are not simultaneously holding. Okay. So what we can do from here is, so we are done with this information. So whatever we have, similarly, so as from this particular part also c to the power n will be greater than a to the power n. C to the power n will be also greater than b to the power n. Mane c is same thing you will get from there also. C is greater than a, c is greater than b. These are the things which you will get from there. Okay. So if you see from here, c to the power n is given. Now let's come down to this equation. So we are done with the first equation. Come down to this equation. C to the power n is given. A to the power n plus b to the power n is c to the power n. Let's write this as c to the power n equals c to the power. Let's write this c to the power n in terms of n and m so that we can use these conditions. These are observations what we have made. Informations, hidden informations what is given. So c to the power n I'll write in such a way that these informations whatever we have derived will be utilized. When I write this c to the power n in terms of n as well as in terms of m. So c to the power n minus m into c to the power m, let's say. We can write this c to the power n as c to the power n minus m multiplied by c to the power m. We can write it in this manner, obviously. In terms of n and m we are writing. Why we are writing in this format? N minus m. Because you have considered this assumption n is greater than m, which means n minus m is greater than 0. M minus m is greater than 0. So likewise, so some terms of n minus m is there. So let us write this in terms of n minus m. C to the power n minus m into c to the power m. Now what is this c to the power m from this first equation? A to the power m plus b to the power n. Write this down, c to the power n minus m. Automatically your flow will come if you just solve by taking observations and keeping on just writing down whatever is given. Automatically this flow of solving this thing will come. Like c to the power m is there. We know the value of c to the power m. Let's write down. Let's see what we can get from there. C to the power m. That's given. So c to the power n is now c to the power n minus m into b to the power m plus a to the power m plus b to the power m. Right? Also you are getting some sort of c to the power n minus m terms as well. Isn't it? One thing we can do from here, in fact, you have got this inequality, you can further simplify this inequality. Further you can simplify this inequality. You have c to the power n minus m, so definitely c to the power n minus m will be obviously greater than a to the power n minus m. And c to the power n minus m will be obviously greater than b to the power n minus m. Why we are doing this thing? Because we have c to the power n minus m terms over here. Some sort of c to the power n minus m terms are there. So definitely you have to bring some inequality, show that this is not holding. We'll show that you will have a contradiction, that whatever assumption we have considered, that is wrong. Okay. So c to the power n minus m into a to the power m plus b to the power m. So we are getting this relation because see n minus m is positive, so definitely we can raise the power. There will be no problem if you raise the power. No sign change or orientation will not be changed. Reason being n minus m we have considered to be positive. Okay, so orientation won't be changed. That is for sure. C to the power n minus m is greater than a to the power n minus m, and c to the power n minus m is greater than b to the power n minus m. So c to the power n minus m into a to the power m plus b to the power m. Okay. So definitely we can get some inequality, or let's simplify this thing further. You can multiply this thing. You can multiply and write this as c to the power n minus m multiplied by a to the power m plus c to the power n minus m multiplied by b to the power m. You can multiply this and write it in this format. Obviously, just simply multiplication, basic multiplications, nothing else. Okay. And from here we get this inequality. We know that c to the power n minus m is greater than a to the power n minus m, and c to the power n minus m is also greater than b to the power n minus m. Right? So put these values, which means that this is greater than c to the power n minus m is greater than a to the power n minus m. So write down a to the power n minus m in the place of c to the power n minus m. Simple inequality, nothing else. Basic inequality bolchi. You have c to the power n minus m greater than a to the power n minus m. So obviously whatever you multiply this thing, okay, multiply a to the power m over here on both sides. So obviously this will be still be greater than a to the power n minus m multiplied by a to the power n. So that's what we are doing over here. So into a to the power m. That is fine. We have a to the power m over here, but we have showed that c to the power n minus m is greater than a to the power n minus m. That is what we have done. C to the power n minus m is greater than a to the power n minus m. Plus, again, with b also you have one more relation. C to the power n minus m is greater than b to the power n minus m. Right? So this is once again, this term is also greater than b to the power n minus m. Okay. into b to the power n. And if you simplify this relation, a to the power n minus m into a to the power m plus b to the power n minus m into b to the power m, if you simplify this thing, this will turn out to be a to the power n plus b to the power n. Mm cancel out, b to the power n, and from here also cancel out, so you have a to the power n. So a to the power n plus b to the power n you are getting from here, which means that initially what you are proving is, you have proved that, let me show over here, you have proved that this is nothing but c to the power n. This is nothing but c to the power n. You have initially proved that c to the power n is basically greater than a to the power n plus b to the power n. You have proved this thing, which is not possible because this is given to be a to the power n plus b to the power n is equals to c to the power n. Mane, it's a contradiction. This is not possible. It's a contradiction. C to the power n is greater than a to the power n plus b to the power n. What you have proved? What you have a to the power n plus b to the power n is equals to c to the power n, which is not possible. Which means that final statement, our assumption is wrong. Let's do one more method. The same question can be done using one more method. Okay, there also you are going to take the same assumptions. What kind of assumptions you are going to consider? So over here in the first case, let's say you have considered, assume that n greater than m. Okay, so in the next process, in the next method, what you can do is you can consider m greater than n. I told you any of this assumption you can consider, either n greater than m or m greater than m. So what you can do in this case is, for the next procedure, for the next method, in fact, you can take this assumption m greater than n. Okay, so suppose you assume that m greater than n, suppose. Okay, so obviously corresponding to which you will have certain equations. You have got certain equations. These equations are given. Is equals to c to the power m. Then you have a to the power n plus b to the power n is equals to c to the power n. You have to show that these are not simultaneously holding for whatever assumptions you are creating. Simultaneously, this cannot be true, right? Obviously, from here also you are getting certain observations. What are the observations in this case? Obviously, a is less than c, a is less than c, b is also less than c. Clearly, we can see from here, a is less than c and b is also less than c, isn't it? Which means basically c is greater than a and c is also greater than b, basically. So that's why when you have this thing, a less than c and b less than c. So if a is less than c, definitely a by c is less than 1, b by c is also less than 1. Okay, a is less than c, which means a by c is less than 1 and b by c is less than 1. A by c is a proper fraction in this case. A by c is a proper fraction, reason being it's mentioned in the question. If you just read the question over here, 3 positive real numbers a, b and c. So these are all positive real numbers, strictly greater than 0. Okay, even m and n are positive integers, those are greater than 0. Okay, so in this case, a by c is a proper fraction. A by c is a proper fraction lying between 0 and 1. It is less than 1, which means it's a proper fraction, right? So in this case, what we do is we will use this property that from the first equation, what we are going to do is, from this first equation, we are going to divide this equation by c to the power m, let's say. Okay, we divide this equation by c to the power m. So this turns out to be, this equation turns out to be a by c whole to the power m plus b by c whole to the power m is equals to 1. Okay, similarly in this equation also we are going to divide by c to the power n. So this turns out to be a by c whole to the power n plus b by c whole to the power n is equals to 1. That is what we are going to do. Fine. Which means that, so suppose over here we have these two equations, simplified version of our equation, and we have this particular relation a by c less than 1 and b by c is less than 1. So from here we are going to derive one conclusion from which we are going to use one property, actually property of inequality, exponential inequality. In fact, if you know, that is fine. It is a very common concept which I am going to use, basic concept which I am going to use over here, basic concept of exponential inequalities. Okay, exponential inequalities, because this is a proper fraction is there. Okay, so and some exponents are there, m and n, definitely. So we are going to use some inequalities because we have generated some inequality format from here, which means that over here a by c, therefore a by c whole to the power m, we can say that a by c whole to the power m is less than a by c whole to the power n, because we have considered this assumption m is greater than n. M is greater than n. Okay. In fact, this is our inequality, what we are going to use over here, because m is greater than n, we have considered, which means that any exponent, if you consider exponential function a to the power m like this, a to the power m and a to the power n. Okay, if m is greater than n, then a to the power m is greater than a to the power n. When this a is greater than 1, when a is greater than 1, and this thing, the orientation will change when a lies between 0 and 1, when a lies between 0 and 1. Common logic, you only think, if you just simply take this function, this is an exponential function you are considering, a to the power m, right, a to the power x, suppose. Okay, a to the power x you are considering, x is greater than 1, sorry, x is greater than y, and a is greater than 1. In that case, inequality will be a to the power x is greater than a to the power y. You take the values of a, simply put the values of a, and simply put the values of x and y to be some values of x and y which is satisfying this inequality, x is more than y or m is greater than n. You can consider any inequality, any values, any specific values, and simply verify this property. And when this is a proper fraction, lies between 0 and 1, orientation of this inequality will get changed. In more formal terms, we can say that this exponential function, if you remember, we have discussed this thing, a to the power x, this exponential function fx is equals to a to the power x. This is monotonically increasing function for a greater than 1. This is monotonically increasing function for a greater than 1. We have seen the graph of this function as well in functions chapter. And when a to the power x is monotonically decreasing function when a is a proper fraction. When a is a proper fraction, it is monotonically decreasing function for this to be proper fraction. So basically the orientation of this inequality will get changed by the definition of monotonically decreasing function. In fact, you can write this as a property. If you want, you can write this as a property. If x is greater than y, okay, then number 1, a to the power x is greater than a to the power y if a is more than 1, and a to the power x is less than a to the power y if a lies between 0 and 1. A lies between 0 and 1. Okay. A to the power x is less than a to the power y. Clear? So that's why we use this property, that since you can write down, since m is greater than n, a by c whole to the power m is less than a by c whole to the power n, because a by c is what? A by c is a proper fraction. Because there are certain restrictions over here. It's mentioned that a, b, c all are positive real numbers. All these are positive real numbers. So which means that a by c is strictly greater than 0. Okay. And a by c, since a by c we have generated this inequality, a by c is less than 1, which means a by c lies between 0 and 1. So it's a proper fraction. So which means that m is greater than n. We use this property, a to the power x is less than a to the power y. So which means that a by c whole to the power m is less than a by c whole to the power n. Okay. Clear? Similarly, we can generate the next inequality as well. Similarly, b by c whole to the power m is less than b by c whole to the power n. Okay. Now, if you add these two inequalities, left hand side with the left hand side, right hand side with the right hand side. So this turns out to be, this will turn out to be a by c whole to the power m plus b by c whole to the power m is less than a by c whole to the power n plus b by c whole to the power n. Adding them, which means this is 1. We all know this thing. This is 1. This one, a by c whole to the power m plus b by c whole to the power m is 1, and 1 is less than 1, which means a contradiction. There's a contradiction. Not possible. 1 is less than 1. This is not possible, right? So our assumption is wrong, that m is greater than n. Okay. This is the thing. Clear? Show up. Chalo, next question. Next. So we are done with this. This was the third question, I think. Third question, second. Okay, so chalo, fourth one. Lots of questions we are going to solve, including ISI questions as well. Let's see some results which you can consider them to be sums actually, but you can definitely use them as results as well. Okay. The fourth one, you can consider them to be results or questions, whatever you feel like. So this is your first result of the first question. Okay. The first result of the first question. The square of any integer is of the form 3k or 3k plus 1. Maybe some of them you have done earlier as well. Let's do once again for practice. The square of any integer is of either of the form 3k or 3k plus 1. How do we prove this thing? Obviously, question of division algorithm, basic question of division algorithm. So suppose we consider an integer, okay, which is of the form 3m plus 1 or 3m plus 2. Okay, since they have mentioned over here, it's 3k or 3k plus 1. So definitely it's better to put b is equals to 3 in the division algorithm, right? Okay, in the division algorithm, we simply put that b is equals to 3 basically, right? So which means suppose you consider a to be an integer. A is an integer, let's say. Okay. So by division algorithm, what is A? A is of the form 3k plus 1 or 3k plus 2. Because you are putting this a value of b in division algorithm, basically you are putting this value of b to be 3, right? And when you are dividing a number by 3, the possible remainders are 0, 1 or 2. And that's what you are getting, 0, 1 or 2. Okay. So for each of these cases, we are going to verify that the square of these integers is either of this form 3k or 3k plus 1. That's what we are going to verify. Okay. So case 1. Case 1 is what happens if A is equals to 3k. So simply put case 1. We have case 1 where A is equals to 3k, let's say, which means that A square is 9k square. Okay, 9k square, which means you need to check the square, right? The square of any integer. So we are squaring. A square is 9k square, which means we can write this as 3 into 3k square, which means that this is ultimately of the form 3k only. This is ultimately of the form 3k only, isn't it? Case 2. A is equals to 3k plus 1, which means A square. What is A square? A square is 3k plus 1 whole square, which means A square is, break this into whole square format. So 9k square plus 6k plus 1, which means you take out 3 common from these two factors. So we have 3 into 3k square plus 2 plus 1, which means this is an integer. So definitely this is of the form 3k plus 1. So this is of the form 3k plus 1. And lastly, we have case 3. Case 3 states if A is equals to 3k plus 2, same logic, A square is 3k plus 2 whole square, right? Which means A square, if you break this into whole square format, so we have 9k square plus 12m plus 4 plus 12k plus 4. So this is basically 9k square plus 12k. We can write this 4 as plus 3 plus 1. We can write this 4 as plus 3 plus 1, right? We are writing this in the form of 3 plus 1, reason being from here 3 gets common. So which means if you take 3 common, so this is 3k square plus 4k plus 1. And here we have plus 1. This is once again an integer. So 3 into k plus 1. So this is once again 3k plus 1 format. Okay. Where k is this thing. Where this capital K is 3k square plus 4k plus 1. So which means that it is either of this form 3k or 3k plus 1. All these are basically some basic applications of division algorithm we have seen before as well. Let's see the next result. So next one says the cube of any integer is of the form 9k, 9k plus 1 or 9k plus 8. We have to prove this. Similarly, by division algorithm, let's use division algorithm. So by division algorithm, what we can say from here, any integer, you consider any integer a, let's say, any integer a is of the form 3k, 3k plus 1 and 3k plus 2. Any integer a is of the form 3k, 3k plus 1 or 3k plus 2. This is by division algorithm. You put the value of b to be 3 basically. And when you're dividing a number by 3, definitely possible remainders are 0, 1 and 2. Again, similarly, case 1. Here they have asked for the cube, so definitely you have to cube this. So if a is equals to 3k, then what is a cube? 3k whole cube, which is basically 27k cube, which is 9 into 3k cube, and that is basically 9 into capital K, let's say, which is a multiple of 9. And that's what we have seen, that 9k, it is of the form 9k, where k is this number 3 into small k cube. Similarly, we see the case 2. Case 2 is what? Case 2 says if A is equals to 3k plus 1. So if A is equals to 3k plus 1, then A cube is 3k plus 1 whole cube, which means A cube, break this, A plus B whole cube. So this turns out to be 27k cube plus 27k square plus 9k plus 1. 9k plus 1. So once again, you can take out 9 common from these three terms. You take out 9 common from these three terms. So what this turns out to be? So whatever this thing is, so this is basically an integer only. So this is of the form 9 into k plus 1. You can take out 9 common from these three terms. So definitely this turns out to be integer only. So this is of the form 9k plus 1, where k is some integer, definitely. Okay. And case 3. Lastly, you will have case 3. What is case 3? What happens if A is equals to 3k plus 2? If A is equals to 3k plus 2, then A cube is what? 3k plus 2 whole cube. Again break this. So this is 27k cube plus 54k square plus 36k plus 8. Which means that this is, once again, you just simply take out 9 common from here. So this is of the form 9k plus 8. So where k is some integer. So you can see that this is either of the form 9k plus 1 or 9k plus 8. And that's what they've asked to prove. So the cube of any integer is of the form 9k plus 1 or 9k plus 8. These are some basic results which we are doing before we skip to the advanced level problem of ISI entrance. Next. So this is your next question. The fourth power of any integer is either of the form 5k or 5k plus 1. This is either of the form 5k or 5k plus 1. Okay. Let's solve this. How do you prove this thing? The fourth power. Now we are going to take the fourth power of this thing. Okay. So basically, so some sort of binomial expansion will be needed. But in case if you know the formula for fourth power, then definitely you can directly use that. Otherwise, you have to binomially break this for the different types of integers. Like suppose in this case, what we do is since they have asked for the fourth power and it's either of the form 5k or 5k plus 1. So it is better in division algorithm, we take the integer of the form 5k, 5k plus 1, 5k plus 2 or 5k plus 4. Means we put the value of b is equals to 5. If you put the value of b is equals to 5, so this turns out to be 5k. The integers will turn out to be 5k, 5k plus 1, 5k plus 2, 5k plus 3 and 5k plus 4. Remainders, possible remainders will be 0, 1, 2 and 3. 0, 1, 2, 3 and 4. Possible remainders will be 0, 1, 2, 3 and 4. Okay. So basically, by division algorithm, what we do, any integer, let's say n, is of the form 5k, 5k plus 1, 5k plus 2, 5k plus 3 and 5k plus 4. So these are the possible integers 5k, 5k plus 1, 5k plus 2, 5k plus 3 and 5k plus 4, because the possible remainders are 0, 1, 2, 3 and 4 and you're putting the value of b is equals to 5. So accordingly you will have how many cases? 5 cases all total. Okay, 1, 2, 3, 4, 5. So each case you have to show that The fourth power of such thing is of the form 5k or 5k plus 1. Let's see. So case 1, you have case 1. So case 1 says what happens if this thing, if n is of the form 5k. If this is 5k, then definitely n to the power 4 is what? 5k whole to the power 4, right? So you can write this 5k whole to the power 4. You can take out one 5 common and write this as 5 into 125 k to the power 4. In this manner you can write, which is of the form 5k only. It's of the form 5k. Okay, it's of the form 5k. So definitely, where obviously k belongs to z integers, so it's of the form 5k. Now if n is equals to, let's say, 5k plus 1, n is 5k plus 1, let's say, then n to the power 4 is 5k plus 1 whole to the power 4. Now see, if you know the formula of this thing, binomial expansion, then you can expand this. Otherwise, you have to derive the formula and just simply put this over here. Maybe by the Pascal's triangle, the coefficients and all the general logic, or just simply put the binomial formula, the main binomial formula for a plus b whole to the power 4. Or definitely, you will find that I have told you one concept. Definitely, you will see that a binomial expansion, whatever you're expanding 5k plus 1 whole to the power 4. So definitely, if you take whole to the power 4, so some sort of terms involving multiples of 5 will get generated. Terms involving multiples of 5 will get generated. In the last, there will be one more term, which is 1 to the power 4, which is plus 1. And your plus 1 indicates your remainder, isn't it? The plus 1, the last, the constant plus 1 minus 1, all these are remainders, which means that if you expand this thing, anyways, if you expand this thing, you will get a multiple of 5. You will get a multiple of 5 plus 1. 1 to the power 4, that is basically plus 1. So plus 1 will get generated, and this stands for the remainder only, which means that this 5k plus 1, this is multiple of 5, which means 5k plus 1, where k belongs to z. So obviously this is of the form 5k plus 1, which is done. You can expand this thing and see as well. You will get some certain terms will get generated, and multiple of 5 will get common, and definitely at the last you will have 1 to the power 4, which is plus 1. Okay, and that's your remainder. Similarly, we have case 3. If n is equals to 5k plus 2, let's say, then we have n to the power 4. Same logic, 5k plus 2 whole to the power 4. Now see over here, you want to expand this thing, you can verify from here itself. Similarly, just like the previous manner, 5k plus 1 whole to the power 4, you will have this thing 5k plus 2 whole to the power 4. If you expand this thing, you will get a multiple of 5 plus, at the last there will be one more term, which is 2 to the power 4, which is 16 plus 16, which is your remainder, isn't it? Plus 16 is what your remainder, which means that you have of this format. Ultimately, if you expand this thing, you will get of this format multiple of this thing, multiple of 5 plus 16. Why plus 16? Because last term will be what? 2 to the power 4. Last term will be what? 2 to the power 4, which is plus 16. I told you the first term is always 5k whole to the power 4, and the last term is 2 to the power 4. In between, there are lots of terms are there. That depends on the binomial expansion. If you have the binomial expansion of a plus b whole to the power n, the first term is always a to the power n. Last term is always b to the power n. So the last term is what? Is a constant, which is your remainder, because your plus 16, that is your remainder. So multiple of 5 plus 16. Clear? And you can further write this 16 as 15 plus 1. 16 as 15 plus 1. Why we write this as 15 plus 1? Reason being 15 is a multiple of 5, which means that this particular 15 is now absorbed in this multiple of 5, with this multiple of 5. It's a multiple of 5 as well, which means that this 15 is now getting absorbed in this multiple of 5. So what we can do is we can write this entirely as 5k plus 1. This is once again of the form 5k plus 1. And lastly, we have case 4. What happens if n is equals to 5k plus 4? Sorry, 5k plus 3. Last case, second last case. This is your second last case. Case 4 is if n is equals to 5k plus 3. Similarly, same logic. N to the power 4 is 5k plus 3 whole to the power 4. Now, if you expand this thing, so you will get multiple of 5 plus 3 to the power 4, which is 81. 9 square, which is 81. Clear? Multiple of 5 plus 81. Multiple of 5 plus 81. Okay. And further, you can write this 80 as 80 plus 1. Further, you can write this 80 as 80 plus 1. Reason being, 80 is a multiple of 5. So that particular 80 is now absorbed in this multiple of 5. Okay. So you have multiple of 5 plus 1. 80 plus 1. So 80 is getting absorbed in this multiple of 5. So definitely, obviously, you will have multiple of 5 plus 1. So multiple of 5 plus 1 means what? 5k plus 1. Same logic, 5k plus 1. So once again, you have this is of the form 5k plus 1. And we have the last case, which is 5k plus 4. Now you all can verify for 5k plus 4. Right? Case 5. You all verify for 5k plus 4. N to the power 4 and verify this. You will get this as a multiple. Same logic. You all can now verify. Okay. So all total 5 cases, you will get either of the form 5k or 5k plus 1. So the fourth power of any integer, write down the conclusion at the end after solving this fifth case, that the fourth power of any integer is either of the form 5k or 5k plus 1. That's all. Question number 5 is a very nice question and a popular one. You will find this question. Probably this is there in your excursion book as well as in your assignments as well. I think this is the exercise problem of your excursion, probably, as far as I remember. Prove that no integer in the sequence 1 1, 1 1 1 1 1 1 and so on is a perfect square. So none of these in the sequence, if you have this sequence of numbers of this format, so none of them is a perfect square. That is what you have to prove. Okay. So in this case, definitely we are going to prove by division algorithm by considering some values of b and all, but definitely in this case also you are going to observe the numbers as well. You have to prove that this is not a perfect square. No integer in this sequence is a perfect square. So if you observe the numbers over here, 11, then 111 and 1111 and so on, you have these numbers. If you observe these numbers, you have 11. 11 is basically, if you can write it in some format, what we can say from here, 11 is 8 plus 3. 11 is 8 plus 3. 11 is 8 plus 3. 111 is basically 108 plus 3. 1111, that is basically 1111. And that is basically 1108 plus 3. Same thing goes for the next one. Yeah, 11111, which is 11,108 plus 3. So every time you see one pattern over here, you're getting this to be 8 plus 3, 108 plus 3, 1108 plus 3, 11,108 plus 3 and so on. So what is the pattern in this case? The pattern, what you're getting from here is each of these numbers is basically a multiple of 4 plus 3. Multiple of 4 plus 3. It's a multiple of 4. I'm saying this because the last two digits you can see that's 08. It's a multiple of 4. Last two digits is 08. It's a multiple of 4. Right? So this is of the form 4k plus 3. This is once again of the form 4k plus 3. This is also of the form 4k plus 3. Because this number is a completely divisible by 4. 08 is there, which means if the last two digits of a number is divisible by 4, then the number is entirely divisible by 4. And you have learned this before as well. So 4k plus 3. And this is lastly, you have 4k plus 3. So all of these numbers in the sequence, we have this to be 4k plus 3. 11, 111 and so on. All these numbers are in the sequence is basically of the form 4k plus 3. Okay. So any integer you can see from here is in this sequence is of the form 4k plus 3. Now see from here, by the division algorithm, you know that any integer is of the form 2k or 2k plus 1 if you put the value of b is equals to 2. In division algorithm, if you are putting the value of b is equals to 2, let's say, then any integer a is of the form 2k or 2k plus 1. All of you know this thing? It's basic division algorithm. We are just saying. So any integer by division algorithm, any integer is of the form 2k or 2k plus 1. You're putting the value of b is equals to 2 in division algorithm. So definitely you will get this form to be 2k or 2k plus 1 because possible remainders will be 0 and 1. Right? Divisor is, you're keeping this divisor to be value of b basically to be 2. So 2k or 2k plus 1, this is possible by division algorithm. So for each case, if we check for each case, let's say for case 1, what we have for case 1? If n is equals to 2k, then n square is 2k whole square, which is 4k square. This is of the form 4k. This is something multiples of 4. And case 2, in case 2, you will see that if n is equals to 2k plus 1, then n square is of the form 2k plus 1 whole square, which means n square, if you expand this thing, so this is 4k square plus 4k plus 1, which is of the form 4 multiples of 4k plus 1. So n square is of the form 4k plus 1. Obviously, k is an integer. So basically, what we are getting from here, the square of any integer is either of the form 4k or 4k plus 1. The square of any integer is either of the form 4k or 4k plus 1. But we have the given sequence of number is of the form 4k plus 3 and not 4k or 4k plus 1. Any integer in this given sequence is of the form 4k plus 3. But we are getting all these squares of integers to be either of the form 4k or 4k plus 1 and not 4k plus 3, which means that this is not a perfect square. Okay, so no integers in this sequence is a perfect square. You can write down the conclusion, since any integer in the given sequence, any integer in the given sequence, is of the form 4k plus 3. Given sequence means this sequence 11, 111 and so on, is of the form 4k plus 3. Hence It is not a perfect square. You can add one more line if you want, that we are getting the square of any integer is of the form 4k or 4k plus 1. 4k or 4k plus 1 and not of the form 4k plus 3. So definitely this is not a perfect square. Clear? Take this down. Chalo, next. Try out this question first, then I'll help out. If n is an odd integer, show that n to the power 4 plus 4n square plus 11 is of the form 16m. Mane multiple of 16. Complete multiple of 16, where m is an integer. Okay, all right. Since he has mentioned this logic, that is also accepted. আমি ওর procedure এ যাচ্ছি, that is in division algorithm you put the value of b to be 4. Okay, in that case there will be certain extra cases, many even cases will be generated which actually had to be omitted basically. Many any integer, if you go by the division algorithm, then any integer, let's say n is of the form 4k, 4k plus 1, 4k plus 2 or 4k plus 3. But in this case, problem will be, because it's mentioned n is an odd integer, you cannot consider 4k. Also, you cannot consider 4k plus 2 because these are even numbers. Multiple of 2 na, so even numbers. So definitely you cannot consider them, which means that you have to consider these two cases. So 4k plus 1. So 4k plus 1, which means basically case 1. Suppose you consider case 1. If n is equals to 4k plus 1, which means n to the power 4 plus 4n square plus 11 is basically 4k plus 1 whole to the power 4 plus 4 into 4k plus 1 whole square plus 1. Put the value of n. Now, if you can expand this, then it will be better. Using binomial theorem, you can expand this thing 4k plus 1 whole to the power 4. Okay, you can expand using this formula, or you can directly use this formula if you know this, a plus b whole to the power 4, which is a to the power 4. Last term will be plus b to the power 4, and in between if you see, this is 4a cube b plus 6a square b plus 4ab cube. 4ab cube. So use this thing. So we have 256 a to the power 4. So 4k whole to the power 4. So 256 into k to the power 4 plus 256k cube. Okay, 256k cube plus 6a square b square. 6a square b square mane 6 into this thing, 6 into 16, that is basically 96k square plus this thing is 16k plus 1. And if you simplify this thing, 4k plus 1 whole square into 4k, that is basically 64k square plus 32k plus 4 plus 11. Now simplify. I think terms of you have to prove that this is of the form 16m. Multiples of 16 you have to prove. Let's see if there is any multiple of 16 getting common from here or not. This is a multiple of 16. You can gradually see from here itself. It's a multiple of 16 only. 256, 96, 16. It's a multiple of 16. So you can write this to be 16k. So 16k and What else? What else we can say? 16k is there, and this term is there, so we can write this to be, now this is a multiple of 16. This much is a multiple of 16. So this is also a multiple of 16, plus this is 11 plus 4, right? 11 plus 4, isn't it? 11 plus 4 and plus 1 over here, and plus 1. 11 plus 4 plus 1, mane 15 plus 1, 16. So 16k plus 16k, you can write this to be entire multiple of 16 only. Let me rewrite this. Okay, ultimately what you're having is, this is basically 16k. Okay, 16k from here, and we have, this is also 16k, multiple of 16. 11 plus 4, 15, and plus 1 over here, which is 16, minus 16k. Ultimately you have 16, multiple of 16 only. Right, na? 16k plus 1 plus 4 plus 11. That is ultimately 16k plus 16, which is 16 into k plus 1, which is 16m, where m is k plus 1, multiple of 16. So similarly, you prove for case 2, I think k 4k plus 3 also, you will get this same logic. Okay, for case 2, what you have to do is, you have to simply put this, n is equals to 4k plus 3. 4k plus 3, if you put n is equals to 4k plus 3, then n to the power 4 plus 4n square plus 11. Again, same logic, 4k plus 3 whole to the power 4 plus 4 into 4k plus 3 whole square plus 11. 4k plus 3 whole square plus 11. Same logic, you can now simply prove this. Next question. Okay, next question. Prove that the difference of two consecutive cubes is never divisible by 2. The difference of two consecutive cubes is never divisible by 2. Let's see how to prove this. Difference of two consecutive cubes is never divisible by 2. So you consider the two consecutive cubes and its difference. You can consider in this manner, n plus 1 whole cube minus n cube. We are going to see the difference of this thing. Let's simplify this thing, n plus 1 whole cube. This is n cube, a plus b whole cube formula. N cube plus 3n square plus 3n plus 1 minus n cube. N cube cancel out. We have 3n square plus 3n plus 1, which is, from here you can take out 3n common. So this is n plus 1 plus 1, isn't it? That's what you're getting. You have to prove that this difference is not divisible by 2. It is never divisible by 2. Now, if you remember, we have done one property. The product of two consecutive integers is divisible by 2. You can see that this is a two consecutive integers, the product of two consecutive integers, n into n plus 1, right? And we have done one property that the product of two consecutive integers is divisible by 2. And this is quite obvious also. Reason being, you have the product of two consecutive integers. Okay. And so definitely this means that one of them has to be even. Right? One of them has to be even. So which means that this is obviously divisible by 2. Clear? Since 2 divides n into n plus 1, 2 divides n into n plus 1, or you can write down that the product of two consecutive integers is divisible by 2. Therefore, what we can say? This expression is of the form a multiple of 2. This will turn out to be a multiple of 2. N into n plus 1 is now a multiple of 2 because 2 divides this number. So it's a multiple of 2. So this entire thing is a multiple of 2 plus 1. So multiple of 2 plus 1. So definitely 2 does not divide this number. This number is of the form multiple of 2 plus 1. Okay. So this is of the form a multiple of 2 plus 1. Therefore, 2 does not divides n into n plus 1 whole cube minus n cube, which means that the difference of two consecutive cubes is never divisible by 2. The difference of two consecutive cubes is never divisible by 2. Done. Chalo, next. We move on to a standard question now. A, B, C are given to be natural numbers such that these two conditions are given: a square plus b square is equals to c square, c minus b is equals to 1. You have to prove that number 1, a is odd, number 2, b is divisible by 4, and number 3 is a to the power b plus b to the power a is divisible by c. Right? How do we prove this thing? And this is, I consider this question to be one of the easiest question. Two conditions are given: a square plus b square is equals to c square, c minus b is equals to 1. Okay, a square plus b square is equals to c square, c minus b is equals to 1. You have to prove that first part is a is odd. Basically, a is odd. Let's see how to prove this. A is odd. So first of all, though, you all can just simply bring this into an equation of two variable only, because you have three values, money a, b, and c is there. What you can do is you can simply find out c. You can find out c from here. What is c? C is basically 1 plus b. So simply put this c over here. So that is basically a square plus b square is equals to b plus 1 whole square. A square plus b square is equals to b plus 1 whole square. Clear? Now simplify this thing. Simplify this thing. A square is a square plus b square is equals to b square plus 2b plus 1. Okay, so b square cancel out. So a square is what? 2b plus 1. Which means, what is the meaning of this thing? A square is 2b plus 1. A square is 2b plus 1 means basically a square is odd. A square is odd. Multiple of 2 plus 1 means what? A square is odd. And if a square is odd, which means a is also odd. A square is odd, which means a is also odd. Clear? So the first part is done. This first part is done now. A is odd now. Clear? A is odd. Or also you can do it in this manner also, in case if you want, you can do it in this manner. Let's say regarding the first part only, I am saying you have this relation: a square is given, a square plus b square is equals to c square. This is given. A square plus b square is equals to c square. You can rewrite from here what is a square. A square is what? C square minus b square. A square is c square minus b square, which means a square is, if you rewrite this, so this is c plus b into c minus b. Okay, and c minus b is given to be 1. So this is 1, which means a square is c plus b. A square is c plus b. Okay. Now, how do we prove that a is odd now? So we try to prove a square is odd. In this case, what will help is this c minus b, this given information c minus b. If you see from here, c minus is given to be 1 basically, right? C minus b you can see that C minus B is odd, right? If C minus B is odd, then definitely one of C and B is even, right? One of C and B is what? Even. Even minus odd is what? Odd. So one of this C and B is basically odd. Or basically one of this particular C and B is even. If one is even, other one is odd. Sum of two even and odd numbers, meaning even plus odd is what? Even plus odd. Odd. Even minus odd, and that is also basically odd. So what we can say is basically if C minus B is odd, why this is odd? Because this is given C minus B is 1. So C minus B is basically odd. So this means that one of the C and B is even. So if one of this is even, then the other one is gradually this will be odd only. Which means that if their difference is basically odd, then we can also say that their sum is also odd. Their sum is also odd. Which means that this particular A square is equals to C plus B. This is also odd. A square which is C plus B is also odd. Okay. So which means that A square is also odd. Clear? A square is also odd, which means that A is also odd. A is also odd. Once again repeat. A square is C plus B into C minus B. Put the value of C minus B, which is 1. So C plus B, you have A square is C plus B. Okay. A square is C plus B. So C minus B is odd basically. C minus B is odd. Why? Because C minus B is given to be 1. So C minus B is odd. Okay. Which means that if C minus B is odd, then one of C and B should be odd, or one of C and B should be even, and the other one is odd, right? One of C and B should be even, and the another variable, another value should be odd, which means that their difference is odd, which means that their sum is also odd. Odd plus even is what? Odd only. So basically their sum is also odd. So if C minus B is odd, which means C plus B is also odd. C plus B is also odd. Clear? C plus B is also odd. So their sum is also odd. Money A square is odd. C minus B is odd implies C plus B is odd, which means A square is odd, which means A is also odd. That's all. That is the proof. Either you prove in this manner by eliminating C, or you prove in this manner. Clear? Chalo, next. So we are done with the first part. Now the second part. So now we have to prove that B is divisible by 4. Okay. We have to prove that B is divisible by 4 now. Let's see how to prove this. B is divisible by 4. Understand this part. To prove B is divisible by 4, mean B is basically 4 into K something, or 4 into lambda, like this. Multiples of 4 we have to prove. B is a multiple of 4. Understand this part. How to proceed here that B is a multiple of 4 basically. Already I have proved that A is odd number. A is an odd number. So what we can do from here is, you know that, what is 2B from here? 2B, or we can find out B from here, right? A square is 2B plus 1. We have simplified this thing. So A square is 2B plus 1. A square is 2B plus 1, which means that 2B is nothing but A square minus 1, which means that B is A minus 1 into A plus 1 divided by 2. We can write it in this manner. B is A minus 1 into A plus 1 by 2. Means basically A square minus 1 by 2. So we are breaking this to A minus 1 into A plus 1 by 2. Clear? And what is this thing? A minus 1 into A plus 1 divided by 2, which means that you have proved that A is an odd number, right? So A is an odd number, which means A is of the form 2K plus 1. Suppose A is of the form, let A is of the form 2K plus 1. Okay. A is of the form 2K plus 1, let's say. which means that if A is of the form 2k plus 1, and if you just put this value over here, so which means B is basically 2k plus 1 minus 1, which is 2k, into 2k plus 1 mane 2k plus 2, right? 2k plus 2 divided by 2. Now 1 2 will be cancelled from here, which you can simplify and write it as 2k into k plus 1 divided by, and this is a cancel only, so 2k into k plus 1, 2k into k plus 1, right? 1 2 gets cancelled from here, you take out 2 common, so this turns out to be 2k into k plus 1. Again, if you observe from here, observation, k into k plus 1, product of two consecutive numbers. Product of two consecutive numbers, and you know that if you consider the product of two consecutive numbers, any one of them must be even, right? The product of, in a product of two consecutive numbers, any one of them must be even, right? Clear? Which means that this particular thing is divisible by 2, and 2 into 2, which means a 4, multiple of 4, so this is of the form 4 lambda or 4k, whatever you call this. Clear? Quite basic explanation I am just simply giving. No use of theorems or whatever, just basic logic we are using. Once again repeat, you have this thing, 2b is a square minus 1. Okay, 2b is a square minus 1, what we have derived from here. Okay, so b is what? Simplify this thing, b is a minus 1 into a plus 1 divided by 2. From this conclusion, what we have made, a is an odd number. Let's say a is basically 2k plus 1 format. So we have b is 2k into 2k plus 2. Take out 2 common from here. So this is of the form 2k into k plus 1. And k into k plus 1, whenever you see of this format, obviously first observation will come to your mind is the product of two consecutive numbers. And the product of two consecutive numbers is basically divisible by 2. So you have 2, 1, 2 in the front, and it's a multiple of 2. Okay, so 2 into 2 lambda, which is 4 lambda. So this entire product is a multiple of 4 basically. But 4 lambda, basically this is divisible by 4. Okay, which means B is of the form 4 lambda. B is of the form 4 lambda, 4 divides B. So B is divisible by 4. B is divisible by 4. We have done this. There is one more way of proving this thing. One more way of proving this thing. In case if you remember the properties of congruences we have done, there is one more way of proving this thing. A small, short way of proving this. We have a square. A square is given to be 2b plus 1. Okay, a square is given to be 2b plus 1. It's an odd number basically, which means a is an odd number. Okay. If you remember one theorem we have done under congruences actually, any odd number whole square is congruent to 1 modulo 8. Generally in the exam hall, definitely this property will not strike to your mind in general, but definitely let's try out this with this property. You have done this property that n, if n is odd, let's say, if n is odd, then n square is congruent to 1 modulo 8. I think we have done this under perfect squares. Perfect square, under perfect square theory, when we were doing the theory of perfect squares, we have done this property. N square, if n is odd, this is only possible when n is odd. And when n is even, possible remainders are 0 and 1. In fact, the property was a single property, what we have discussed in the class, that the property was n square, a perfect square number, is congruent to 0, 1 or 4 modulo 8. 0, 1 or 4 modulo 8. You can see around its lecture number 7, 8 or maybe 7th or 8th in the congruences. Perfect square theory, when we are discussing perfect square theory, you can go through your notes as well. So n square is congruent to 1 modulo 8. Okay. In fact, the property was n square is congruent to 0, 1 or 4 modulo 8. And the property can be subdivided into two parts. What happens when n is even and what happens when n is odd. When n is even, n square was congruent to 0 and 1 modulo 8. And when n is odd, n square is congruent to, sorry, when n square was even, n is even, which means n square is congruent to 0 or 4 modulo 8. And when n is odd, n square is congruent to 1 modulo 8. That was the property actually. So we have this relation n square congruent to 1 modulo 8. Let's see what we can use. If we can use this property over here, you can verify this thing by taking certain examples. Let's say 1, 1, 3, 5, like these numbers, 1, 3, 5, right? 1, 3, 5, their square, 1 square, 3 square, 5 square, let's say 25, 5 square is 25. 25 is congruent to 1 modulo 8. You divide 25 by 8, you will get the remainder as 1. All these numbers, all the odd numbers whole square, you will get this particular thing, this remainder to be 1 when you're dividing by 8. So this means if you can see from here, therefore, this number, since A is odd, basically, it's mentioned A is odd. We have proved this as well. A is odd. So what we can do is we can write this A square. Can we say A square is congruent to 1 modulo 8? We can say this A square is congruent to 1 modulo 8. And basically, or more specifically, if I just write this, A square is basically of the form 8k plus 1. You're dividing by 8, remainder is 1. Divide by 8, remainder 1. So A square is congruent to 1 modulo 8, which is same as A square congruent to 8k plus 1. So A square congruent to 8k plus 1. And A square is basically of the form 8k plus 1. Okay. So A square is of the form 8k plus 1, and you already have simplified A square to be 2b plus 1. Equate these two, let's see what we get. So 8k plus 1 equals 2b plus 1. Previously we have got this. A square is basically 2b plus 1. So 1 and 1 cancel out, which means 8k is equals to 2b. Right? Which means what? B is of the form 4k. B is of the form 4k. B is of the form 4k. Multiple of 4. Which means that B is divisible by 4. Okay, 4 divides B basically. 4 divides B. Clear? Once again, I am giving you 2-3 approaches for a single problem. You are having this particular problem. The first part I gave you 2 approaches. For the second part also I gave you 2 approaches. Any of this approach, but I think the first one, all of you will go with the first one only. All of you will go with the first one because obviously for obvious reasons you have the next part is involving properties. If you remember this, then this will strike, otherwise this won't strike to your mind. Obviously, then you have to go by this manner. The first one. In the first one, we are just simply using basic logic. Whenever you see of this format, k into k plus 1, definitely will strike to your mind that this is the product of consecutive integers, 2 consecutive integers. Okay. Whenever this k into k plus 1, n into n plus 1 will strike to your mind, you see this thing, observe this thing, definitely the first thing which will strike to your mind is the product of 2 consecutive integers. Isn't it? So we are done with the second part of the question. Now the last part. Last part, I'll just simply give you one hint. So first 2 are done. So we are the third one. Now you have to prove that a to the power b plus b to the power a is divisible by c. Is divisible by c. What is the meaning of this thing? A to the power b plus b to the power a is congruent to 0 modulo c. That is what you need to show. A to the power b plus b to the power a is congruent to 0 modulo c. Let's see what we can do from here. So individually we'll find this and then later on we can add the remainders. Okay. we can add the remainders and prove that this is equals to congruent to 0 modulo C basically. So what we can do is we have a to the power b. Let's start with this thing only, a to the power b. A to the power b is there. So we have just now proved that b is of the form 4k, right? Multiples of 4 basically. So let's replace this thing. A is equals to a to the power b is equals to 4k. So a to the power 4k. Okay, a to the power 4k is there. Now what we can derive from here? Anything we can derive from here? Anything we can derive from here? Definitely we can derive from here. Reason being what is given. Observe what is given. A square is given, right? A square, any relation between a square is given, isn't it? Any relation between a square is given. Along with this relation, c minus b is equals to 1. Meaning ultimately, this relation is given a square to be c plus b. This relation. A square is c plus b. Okay, so let's see from here. We can write this in terms of a square into a square whole to the power 2k. Right? So we have this relation a square which is c plus b. Let's see what we can derive from here. Also we have got this as well, c minus b is there, c minus b is equals to 1. Okay, a square is c plus b and c minus b is equals to 1. These are given over here, right? So what we can do is let's solve this. Let's solve for a square. You need a square from here, the simplified version of a square in terms of a single value. So let's simplify this thing. What we do is let's add these two. Let's add these two equations. Let's see what we can get from here. If you add these two, you will get 2c is equals to a square plus 1. 2c is equals to a square plus 1. PB cancel out definitely. So we have 2c is equals to a square plus 1, which means that a square is 2c minus 1. A square is 2c minus 1. So let's put this value of a square as 2c minus 1 over here. Let's see what we can get from here. What is this? 2c minus 1. So this is of the form 2c minus 1 whole to the power 2k. 2c minus 1 whole to the power 2k. Okay. So basically, you are going to see that what is the remainder when this is divided by 2. So this is of the form 2c minus 1 whole to the power 2k. What is the logic? What is the logic in case of expansion and the remainder logic? You expand this thing, whatever is the constant term which is left out at the end, that is your remainder, isn't it? Whatever is the constant term, what is left out at the end, that is your remainder. That's what we have seen in the previous cases as well. You expand this thing, and whatever is the last term which is remaining, in this case, in binomial expansion, if you want to expand in terms of binomial expansion, definitely whatever is the last term, the constant term basically, that the constant term left out at the last is your remainder only. So what we can say is, if you want to find out the remainder when divided by c, so what we can say from here? What is the remainder? Remainder is of the form minus 1 to the power 2k. Minus 1 to the power 2k, isn't it? Minus 1 to the power 2k. Reason I am saying this thing because that is the last constant term which you will get in any binomial expansion, right? If you expand this thing, you will get the last term to be minus 1 to the power 2k. So minus 1 to the power 2k is there, which means basically even powers are there, which means this is 1 only. What is the remainder? Remainder is 1. Clear? That's the procedure what we say. We have seen in the previous cases as well. And similarly, this is your remainder basically, right? So we have to deal with the remainders because we have to show that a to the power b plus b to the power a is congruent to 0 modulo c. So you are dividing by c basically, right? You're dividing by c. Dividing by c, and what is the remainder? So similarly, what you can do is b to the power a. Similarly, check for b to the power a. Okay. What you will do for b to the power a? Same logic. We have certain given things we have to derive from here itself, right? Which one? This one? This step? Okay. You're expanding this thing. If you expand this thing, you have 2c minus 1 whole to the power 2k. You will get the multiples of c. All c terms will get common, right? All c terms will get generated. So c terms will get generated and you are dividing by c, isn't it? Multiple of c terms will get generated. So c terms and the last remaining constant term will be minus 1 whole to the power 2k. Isn't it? Clear? Now it's clear. Constant term is remaining to be minus 1 to the power 2k. And your constant in division algorithm, you see 2k plus 1. 2k plus 1 means what? Divisor 2, remainder 1. Clear? So plus 1, whatever is left out, 2k plus 16. 16 is the remainder. 2k plus 8. 2k plus 3. 3 is the remainder. So these are all remainders basically. The constant term which is left out is what? Is basically remainder. So that's what we are getting from here. So minus 1 to the power 2k, which is 1. Now let us come down to this b to the power a. So if you have b to the power a, so we have, once again, you have to bring this in terms of c first, because they have asked you to find out what is remainder. Mane prove that this is divisible by c, modulo c. A to the power b plus b to the power a is congruent to 0 modulo c. Okay. So let's see from here, we have b to the power a. If we can bring this b in terms of c, what is b? B to ekhane dewa ache in terms of c. Easily you can get from here, what is b? B is nothing but c minus 1. Easily you will get this from here itself. B is basically c minus 1 from here itself. So c minus 1 whole to the power a. Okay. C minus 1 whole to the power a. Again same logic. What is this thing? Minus 1. The remainder will be what? Minus 1 whole to the power a. But whatever is the last term, that is your remainder. Constant term. Constant term is your remainder. Remaining are multiples of c. All terms will be including c. So c into something, multiples of c plus basically this thing will be 1 to the power a. Minus 1 to the power a basically. Last constant term will be remainder. So minus 1 whole to the power a. Now in this case, problem will occur. Is a odd or even? Is a odd or even? Definitely odd. We have proved this already. A is odd. Pata galo. A is odd. We have proved this in the first part only. A is odd. So using this only we can say that this is equals to minus 1 only. Remainder is minus 1. What they have asked to prove? A to the power b plus b to the power a is congruent to 0 modulo c basically. So can you see that the first remainder is 1, next remainder is minus 1. 1 minus 1 is what? 0. Isn't it? 1 minus 1 is 0. So a to the power b plus b to the power a is divisible by c.